To this series of lectures in marine hydrodynamics. In the last lectures on waves, we have concentrated on fluid flow, where the fluid was assumed to be incompressible as well as inviscid. In fact, earlier we have seen the case of Euler equation, or in the case of Bernoulli's equation, also the flow we had assumed the fluid was inviscid in case of Euler equation of motion, and in case of Bernoulli's equation motion, the flow field was considered conservative and the motion was assumed irrotational. And today's lecture will go a little more general way. We will assume that as if the fluid is viscous, then what will happen to the equation of motion. As you know that in case of there are two major equations satisfied by every fluid. One is the equation of continuity, the other is the equation of motion. And equation of continuity says that it comes from the conservation of mass, whereas the equation of motion comes from the law of conservation of momentum, and again which is also comes from the Newton's second law of motion. So, before going to the detail, let us discuss what are the various forces that act on a fluid element, and then we will talk about various parameters which are very influential in judging the fluid characteristics. So, to do so, let us talk about the various forces acting on a fluid element. When you look at the various forces acting on a fluid, it immediately comes to mind the inertia force, we have the viscous force, then we have the gravitational force, that is the gravity force, then we have the pressure force, basically this is the act on the surface of the body, then we have something called elastic force, and then we have something called surface tension force. So, these are some of the major forces which acts on a fluid element and a fluid. Then out of this there are certain numbers that we call, which are the ratio of two of these forces, and I call these numbers, there are some non-dimensional numbers. Based on these forces. Because these non-dimensional numbers, they signifies the role of the fluid character, role of the particular type of motion and a particular type of fluids. And we have seen that in case of Euler equation, inertia force, viscous force was negligible, whereas there was a gravitational force, there was inertia force, there was a pressure force, whereas elastic force was not present, surface tension force was not present, and viscous force was not present. Now, we look at the non-dimensional numbers based on these forces. So, the first thing comes to the, that is called one of the number which is called the Proud number. And it is basically, if you look at the Proud number, basically it is a measure of the ratio of the inertia force to that of the gravity force, call it Fi by Fg. So, that basically the inertia force to the gravity force, and you can say that this is nothing but V by root GL. G is the acceleration due to gravity, that is the gravitational constant, L is a characteristic length, and U is V is called the characteristics velocity, component of velocity. And then this Proud number is become very important when we deal with the flow when there is a surface tension, when there is a free surface, flow associated having a free surface, or even if an interface, when there is a free surface there exists an interface between two immiscible fluid. This Proud number plays a very important role, particularly if you look at the motion of a ship in water or any submerged body, the Proud number plays a very significant role. And more important are the problems associated with the dams, channels, and spillways. This Proud number plays a very, because here the surface elevation plays significant role rather than, and the gravitational flows plays significant role than even if the viscous force. This is what Proud numbers importance. Now another number of this type is what we call the Reynolds number. Because this, as I mentioned, that these forces plays very significant role in characterizing the flows. Then if you look at the Reynolds number, it is again the ratio of two numbers, that is the inertia force, I denote it by Re, it is a ratio of the measure of the inertia force to the viscous force, and often we write it as rho u L by nu. Mu is the dynamic coefficient of viscosity, rho is the density, u is the characteristic fluid velocity, and L is the characteristic length. So, this is a Reynolds number, and this number in fact when it is it can vary between 0 to, it can be 0 very small, or it can be very large, and particularly when you think of flow in pipes, Reynolds number play a very significant role. On the other hand, the pressure change along the pipe are small, so the pressure force does not make much difference. In the same way, if you look at surface tension forces, because in case of pipe flows, surface tension forces are negligible, are not considered, because there is not a second surface where, or second fluid where the surface tension effect will be visible, because there is only one single fluid. Unlike if you consider a meniscus or a tube, you have always the rise is because there is a air, and here there is a fluid. So, what happens, because of the difference in pressure on both sides, there is a rise in the fluid velocity along the two sides of the wall, and which is not case in case of a pipe flow. Similarly, so here the inertia force plays a significant role, and in addition to the viscous force, compared to the in addition to the viscous force. Similarly, the buoyant forces are also there, they are also not equally important. Similarly, if you look at, and as I mentioned that this depending on the whether the inertia force is large or the viscous force is large, again we characterize the flow, whether it is a laminar flow, whether it is a turbulent flow, and whether it is a highly viscous flow, or so various types of flow can be defined based on this Reynolds number. There is another number which is called Euler number. Again, Euler number is defined as the ratio of two forces. It is the ratio of the inertia force to the pressure force. And this Euler force is important, particularly when there is a cavitation. We all know that there is a region when you have seen that in case of the formation of cavity, when the pressure becomes negative and the cavity formation takes place, and near in cavitational flows this Euler number becomes very important. Plays a significant role. And the ratio of the inertia force to pressure force in cavitational flows, the Euler number plays a significant role. Similarly, we have some of the other there is something called Mach number. Particularly when the fluid is become in compressibility, this is more important for compressible fluid. This occurs at high speed flow or motion of an object like jet, airplanes, projectiles through air. When it passes through a subsonic region, a subsonic speed, this Mach number plays a significant role. Then we have this Weber number. Then this Weber number is again a ratio of the inertia force to the surface tension force. Ratio of inertia force to surface tension force. And particularly in physical model testing for a channel or for a harbor, these forces are plays a very important role. This is Weber number. Here the viscosity is not that important compared to the surface tension effect. Now then we have something called Rossby number. Rossby number is an important number when you consider the geophysical fluid flows. Basically, its velocity, which this is associated with the velocity to ratio of velocity to angular velocity. Particularly, most of the geophysical fluid flow problems, in which are more important in for oceanographers or atmospheric science, they are more important to deal with problems associated to oceanography or atmospheric science. Is Rossby number, and particularly where the centrifugal and centripetal forces are more important in this case. And then we have Strouhal number. And this is again, it is important basically when flow around globe bodies. Particularly where vortex shading takes place, vortex formation and shading. Shading takes place. These are some of the important non-dimensional number. There are other numbers depending on when the flow is in a magnetic field, or sometimes we call it viscoelastic fluid, or even if sometimes we talk about poroelastic fluid. So, in such cases there are several other numbers, which non-dimensional numbers, which play significant role anyway, but we will not go to those details. Rather, with this basic background, because the course here is they emphasize numbers which are important to marine environment. So, these are the things which we emphasize. With this understanding about the various forces and the various non-dimensional numbers, let us look at the will derive the Navier-Stokes equation of motion. In fact, the Navier-Stokes equation of motion is again, as I said, that it is a generalization of the Euler equation of motion. Euler equation is a generalization. Here viscosity is neglected in viscid fluid, whereas in this case Navier-Stokes equation of motion this is suitable for viscous fluid. In fact, here also. So, when the fluid is incompressible, what happens? So, from we all know the from Newton's second law, from Newton's second law of motion, we have rho dq by dt, by that we have already seen that is equal to sigma f e x t. So, it is a combination of all the external forces that is acting, and this is the rate of change of linear momentum is equal to the total force. And as we have seen that there are several forces which act on a body. In case of the Navier-Stokes equation, here we will emphasize the three forces, that is, one is the pressure force, one is the body force, and that body force sometimes called the gravitational force, and plus another is the viscous force. So, these are the three forces. When in case of, in fact, in case of one is the pressure force or surface pressure force, this is the gravitational force or the body force, and this is the viscous force. This is important in case of Navier-Stokes equation, but in case of Euler equation viscous force will be contribution will be negligible. So, now to do this, and then if I simplify further this, then what will happen, that my rho del q bar divided del t plus rho into q bar dot del, this is the left side part, and the right side becomes minus grad p plus tau double bar plus rho g bar. And if I simplify, look at the individual terms, this is called the local time rate of change of momentum. This terms refer to the convective change of momentum, and then this term is the net pressure force, and this is the net viscous force, and finally, this is the net gravitational force, which is called the body force, gravity force or gravitational force. So, these are the various forces acting on it. Now, again, what is tau double bar? Tau double bar is basically called the stress tensor. I will define what exactly it is. So, it is, since it is a stress tensor, it has the 9 components, phi 1 phi 2 tau 3 tau 1 3. These are called the stress tensor associated. In fact, it is Stokes is the stress tensor. In fact, it was Stokes in 1845, he gives a very postulated a linear correlation between provided a linear correlation for an incompressible fluid. For an incompressible fluid. And what was Stokes postulate was, the Stokes postulate was tau double bar equal to mu times q bar plus gradient of q bar. It is the transpose of this, and this is what Stokes postulate what, and where mu is the dynamic coefficient of viscosity. Dynamic coefficient of viscosity of the fluid. And this stress tension has, it has 3 normal components, that is tau 1 tau 2 tau 3 and the 6 tangential component, that is tau 1 tau 2 tau 3 tau 1 3 tau 3 2 tau 2 3. These are, so it has basically 6 tangential component, and the stress tensor has, it has 3 normal component and 6 tangential component. If we simplify this stress tensor again, what will happen? Now, we know that the grad of q bar, if you look at this, then you can, this is given by your del u by del x, del v by del x, del w by del x, then you have del u by del y, del v by del y, del w by del y, and the third is del u by del z, del v by del z, del w by del z. And you look at the transpose of this, what will happen to the gradient of q bar transpose? If you look at this, then this gives you again del u by del x, del v by del x, del w by del x, and then del u by del y, del u by del z. This will remain as a del v by del y, and then it will be del v by del z, del w by del y, del w by del z. So, if I, then what will happen to my tau, the stress tensor itself, tau double bar, and that will give me, if I combine this one, it is mu times, tau double bar mu times. If I add these two things, that means, so I will get 2 del u by del x, then this becomes del v by del x plus del u by del y, and the third component is del w by del x plus del u by del z. Similarly, here you will have del u by del y plus del v by del x, then you have 2 del v by del y, and the third component will be del w by del y plus del v by del z. and then the third component it will be del u by del z plus del w by del x. Then we have del v by del z plus del w by del y, and it is 2 times del w by del z. So these are the normal component and these are the tangential component. So of the stress tensor, and if you just compare them, you can go for, because if I say from this we can easily find out, because the stress tensor tau double bar, if I put it component wise, tau 11, tau 12, tau 13, tau 21, tau 22, 23, tau 31, tau 32, tau 33, then I can get the individual component of basically the 3 normal stress component. I can compare with the previous expression for tau, and I can get the 3 normal component and the 6 tangential component of the stress tensor. So if by doing so, then what will happen if I simplify further? I will take the divergent of tau double bar. What will happen? And this is you can write it as a summation of I is equal to 1 to 3 del by del x I tau I k. Suppose I look at the x component and I substitute for this 1 sometimes we call it is basically tau x x, tau 1 2 is tau x y, tau 1 3 is tau x z. Similarly, we can have tau 2 1, tau y x, tau 2 2 is tau y y, tau 2 3 is tau y z, and similarly we can proceed ahead with the tau 3 1, tau 3 2 and tau 3 3. This will be of course tau z x, tau z y, this is tau z z. So this and this, they are the x component, sorry, the normal component, and the rest are the tangential component. Sometimes this is use this notation or this notation. So if you look at the normal component, the x component of the stress tensor, then this will be divergent of this, then it will give you tau I k, and substitute for tau I k as nothing but in terms of x x, and for any k, then what will happen, x component means k is 1. So in that case you can easily see, and again substitute for the individual expression for from the Stokes postulate, then what we will get, this will give us mu times, okay, I simplify a little, this will give us del by del x tau x x plus del by del y tau x y plus del by del z tau x z. And this further simplification, because I substitute in terms of Stokes theorem, Stokes postulate rather, that will give me mu times del by del x tau x x is 2 del u by del x plus del by del y tau x y is nothing but del v by del x plus del u by del y plus del by del z, this is tau x z, that is del w del u by del z plus del w by del x. And if I simplify further, because I will take mu into, I will take one component from here out of 2, so that will give me del square u by del x square, and from here I will take this component plus del square u by del y square plus del square w by del sorry, del square u by del z square, then plus, then I will have mu times, I can write it as a del by del x, del u by del x plus del b by del y plus del w by del z. So, this gives me, because this quantity is nothing but divergent of q. If the fluid is incompressible, this part is 0. Once this is 0, then what will give me for an incompressible fluid, the x component of the stress tensor, the divergent of the x component of the stress tensor, I get mu, rather I will call it del square u, and u is what? U is the x component of the velocity vector. In a similar manner, if I proceed, y component I will get it mu del square v and del dot, the z component I will get it mu del square w, and if I combine this, so if I combine this, then I will get del dot tau double bar equal to that will give me mu del square q bar. So, this becomes my forces, that is the viscous force. So, if I substitute for this in the equation of motion what I proposed in the beginning, so that will give me rho del q bar by del t plus q bar dot del into q bar equal to minus grad p plus mu del square q bar plus rho g bar, and this becomes my equation of motion for viscous and compressible fluid. For viscous and compressible fluid, and sometimes we call this as Navier-Stokes equation of motion for incompressible viscous fluid. And we have, since the fluid is incompressible, we have divergent of q bar is 0, that is the equation of continuity, and this is the equation of motion. So, this is equation of continuity, this is equation of motion, and this is often we call this as the for the Navier-Stokes equation of motion for incompressible viscous flow. And here the additional term is this, whereas if this term is absent, then we call this as the Euler equation. In fact, the approach we have seen the derivation of Euler equation, that is the rate of change of linear momentum is the total force. The same approach, same Eulerian approach can be used, only thing that when we calculate the total force, there is another additional term, that is the viscous term which comes into picture, and this viscous terms comes from the, is based on the assumption of the Stokes, basically based on Stokes postulate. It is one of the simple derivation. You can find this same thing in various textbook in a very elaborate manner by considering the forces acting on the fluid element in by considering in the Cartesian coordinate system, but this is one of the most lucid and simplified manner of looking at the of looking into the equation of motion. Now, I will further simplify this by considering that let us have a, because G is a constant, if the gravitational force is constant and rho is constant, if I assume in most of the cases we assume the fluid density is constant. So, in such situation I can always write P star equal to P minus rho G r, and then r is the position vector. So, then you can, it can be written as d cube r by, the equation of motion can be written as d cube r by dt is equal to minus 1 by rho grad P star and plus nu del square q r. So, this is also another form of writing the same thing when the fluid motion is assumed, fluid is assumed to be incompressible, particularly when the flow is of constant density. Now, before going further, let us say classify, we will classify various, rather classify the, rather I call it classification of flow problems. Of flow problems. If you look at the classification of the flow problems, here few things comes into mind, and based this classification is always based on the flow characteristics and degree of complexity. Degree of complexity of the fluid. So, one of the thing is that whether the flow is laminar or turbulent. Flow is laminar or turbulent. In case of a laminar flow, the fluid characteristics, they follow the, like the fluid particle follow a particular path or a direction when the fluid flows, but in case of a turbulent flows, the fluid, their motion is random or very irregular in nature. One of the typical example of a laminar flow is like it is a fluid particle trajectory is always in, you can predict it in case of a laminar flow, like when a group of soldiers, they are marching on a particular, on a bridge or maybe on a field. On the other hand, if you look at the turbulent flow, you can compare the same thing like a group of pilgrims, those who are moving towards a religious site, either before visit or after visit, or maybe particularly after coming out from a, the pilgrims when they come out of from a religious site, they just move in a very random manner, and the same flow, same can be compared with the turbulent flow. On the other hand, this is like a, as I mentioned, that a group of soldiers, they are marching on a bridge or maybe in a field. So, this is the, from this it can be clear how irregular the turbulent flow pattern can be and how regular the laminar flow can be. Another second example is time dependence and transient motion, second type of flow. Time dependent flows, that is one is steady, the other I can call it as a transient flow. Then we can have the flow field, nature of the flow field. It can be parabolic or elliptic. The flow field can be parabolic or elliptic in nature. Then dimensionality of the flow field. Dimensionality of the flow field. If I dimensionality of flow field. and here there are 3. It can be 1D fully developed flow, 1 dimensional fully developed flow, or it can be 2 dimensional accelerating flow, or it can be 3D completely flow, or it can be 3 dimensional complete flow, 3D complete flow. So, when it comes to dimensionality, these are the 3. Then some of the other things, other characteristics are the flow can be Newtonian or non-Newtonian. The flow field can be isothermal, the flow field is isothermal or temperature dependent. Another type of flow can be, it can be a single, the flow is single phase or a multi-phase flow. So, these are some of the various characteristics, and when you look at the degrees of complexity, some various types of flows they can be. Then the question comes, are we going to discuss all these kinds of flows? No. In principle, I say no, and in fact, it is not always possible to discuss all these things in a series of in a particular course. Rather, what we do emphasize, will consider some of the flows where which can be discussed, very simple flows. We will only discuss some of the simple flows. If we will discuss some of the simple flows, then the question comes whether these kind of simple flows where we can get a closed form solution. Then the obvious question comes, if I will some of the simple flows where I can get a closed analytic form of solution, or maybe some of the flows which only have semi analytic solution or maybe approximate solution, then why it is important to analyze all the simple flows again, which has already been solved? No, this gives us these are the following, some of the reasons are that when we analyze a simple flow, it is better understanding of the flow characteristics, understanding about fluid dynamics, about basic fluid flow problem, and for better comparison between unknown results with new solutions, new results. And the third thing I will say, as a starting point, in understanding problems associated with the real world. So, because these are some of the reasons why often in a classroom simple flow characteristics of very simple problems are discussed. Now, with this understanding, let us look at what is a, if I look at the Reynolds number, particularly RE. As I mentioned, this depends on two ratios, it is the two quantities. One is the basically this is the ratio of the inertia force to the viscous force, and this is also often called it as rho u L by nu, rho u L by mu. Now, what will happen this Reynolds number if Re tends to 0? Let us see what happens. If Re tends to 0, that means we have rho u L by mu will tend to 0. So, what are the possible things that when it will tend to 0? This factor, there are 4 possibility. So, rho u L by mu tends to 0, which implies I can consider 4 possible things. Either the mass is rho is tending to 0, I may have u tend to 0, I may have a situation when L is tending to 0, or I may have a situation when mu tends to infinity. What physically does it mean? So, here when rho tends to 0, I say 0 mass or mass is negligible. Mass is negligible, or it can be very slow motion. U tends to 0 means motion is very slow. Motion is very slow, and when I say L tends to 0, the length scale is very small. And when I say mu tends to 0, that means I look at highly viscous fluid. So, these are the question comes when R is tending to 0, and in fact, so these are sometimes associated with, sometimes we call this as creeping flows. When R tends to 0, the associated flow we call it creeping flow, or we call it slow fluid flow. Fluid motion is very slow. And here in a natural way, the inertia term is because Re tends to 0. So, if it is a ratio of 2 forces, that means the inertia term is because it is the ratio of 2 forces, inertia force to viscous force, inertia term is negligible, and viscous force is dominating compared to the viscous force. And hence, what will happen to the in such situation when inertia force will be negligible to the compared to the viscous force, then if I look at my Navier-Stokes equation of motion for incompressible fluid flow, I will have grad of P will be mu into del square q bar, because the inertia term is negligible. So, this will be the typical equation for a creeping flow motion, and again we have divergent of q bar equal to 0, because this is the equation of motion, and this will give me the equation of continuity, because we have fluid is incompressible, or fluid is incompressible and flow is, and this is sometimes we call it as Stokes flow. Or slow motion. Now, if I will do one thing, I have grad P is mu del square q bar. What will happen if I just say that? That means, if I introduce u, introduce the stream function psi, so u will be del psi by del y, and I will v will be the component of velocity will be minus del psi by del x. Then what will happen to we have grad P is mu into del square q bar. So, then this gives me del p by del x, what will happen, mu del square u by del x square plus del square u by del y square. If I look at this, simplify this and I substitute for u is equal to, so what will happen to this will be, so if I said del square p by del x del y, that will give me mu del square del q u by del x q plus del q u by del p by del y, sorry, this will be del x square del y plus del y q del y q, and then again I have my u is equal to psi y. So, I will put it mu, I can call it del fourth psi by del x square del y square plus del fourth psi by del y fourth. Similarly, if I look at the other component, that means del p by del y from this, that will give me mu del square b by del x square plus del square b c by del y square, and then that will also give me del square p by del x del y. This will give me mu del x del y. So, it will give me del q by del x q plus del q by del x del y square, and v is nothing but minus del psi. Okay, let me call this v, and this is again I will call it v is minus del psi by del x, and that will give you minus mu times del fourth by del x fourth plus del fourth by del x square del y square into psi. So, if I set del square p by del x del y here, just say that both are same, the left sides are same, then the right sides will be same, that will give me del fourth by del x fourth plus 2 del fourth psi del fourth by del x square and del y square plus del fourth by del y fourth, psi will be 0, and which I can write it as del square of del square psi 0, that is same as call it as a del fourth psi, that is 0. So, that means when the motion is so, when the Reynolds number is small, then the stream function psi will satisfy the biharmonic equation. It can be same way, if you eliminate a p, eliminate rather from the equation of motion, if you eliminate rather q, it can be seen that p also satisfy the condition del square p is 0. That means, the pressure satisfy the Laplace equation, here the stream function satisfy the biharmonic equation. So, these are the two equations satisfied, and that is for the when the motion is slow, or we say for creeping flow motion, the Laplace equation, the pressure satisfy the Laplace equation, whereas the stream function satisfy the biharmonic equation, and this is one of the very simplest solution associated with the viscous fluid flow. Particularly, this is whole good, particularly when the fluid motion is slow, and we call it creeping motion, sometimes we call it Stokes flow. With this, we will stop here today. In the next class, we will come to simpler solution associated with Navier-Stokes equation. We will analyze several cases, very simple cases, particularly as application of the Navier-Stokes equation, before going to little more complex problems. And these simple problems will illustrate nicely the various application of the Navier-Stokes equation. With this I will stop here. Thank you.